The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, recall that yesterday we saw, no, 2 days ago, we learned about the curl of a vector field in space. Okay? And we said the curl of F is defined by taking a cross product between the symbol del and the vector F. So concretely, the way we would compute this would be by putting the components of F into this determinant and expanding, and then getting a vector with components ry minus qz, pz minus rx, and qx minus py. So I think I also tried to explain very quickly what's the significance of a curl. So just to tell you again very quickly, basically, curl measures, if you imagine that your vector field measures the velocity in some fluid, then the curl measures how much rotation is taking place in that fluid. So measures the rotation part, we should say the rotation part of a velocity field. So more precisely, the direction corresponds to the axis of rotation. And the magnitude corresponds to twice the angular velocity. Okay, so, well, I mean, just to give you, a few quick examples, if I take a constant vector field, so everything translates at the same speed, well, then obviously when you take the partial derivatives, you'll just get a bunch of zeros, so the curl will be 0. If you take a vector field that stretches things, let's say, for example, we're going to stretch things along the x-axis. So that would be a vector field that goes parallel to the x direction, but maybe, say x times I, so that when you're in front of a plane of a blackboard, you're moving forward. When you're behind, you're moving backwards. Things are getting expanded in the x direction. Well, if you compute the curl, well, you can check each of these terms is again going to be 0. There's no curl. This is not what curl measures. I mean, actually, what measures expansion and stretching is actually divergence. If you take the divergence of this field, well, you'll get 1 plus 0 plus 0. Looks like it will be 1. So in case you don't remember, I mean, divergence precisely measures this stretching effect in your field. And on the other hand, if you take something that corresponds to, say, rotation about the z-axis at unit angular velocity, so that means you'll be moving in circles around the z-axis. So one way to write down this field, let's see, so its z component is 0 because it's moving, everything is moving horizontally. And in the x and y directions, if you look at it from above, well, it's just going to be our good old friend the vector field that rotates everything at unit speed. And we've seen the formula for this one many times. The first component is minus y, the second one is x. Okay, now if you compute the curl of this guy, you'll get 0, 0, 2, or if you want, 2k. And so k is the axis of rotation, 2 is twice the angular velocity. And now, of course, you can imagine much more complicated motions where you'll have, for example, if you look at the Charles River very carefully, then you'll see that the water is flowing, generally speaking, towards the ocean. But at the same time, there are actually a few, eddies in there, and with the water swirling. And those are the places where there is actually curl in the flow. Yes? I don't know how to turn on the lights a bit, but I'm sure that there is a way. Does this do it? Is it working? Okay. You're welcome. Okay. Hopefully it's easier to see now. So, okay, so that was about curl. Now, what does curl, why do we care about curl besides this motivation of understanding motions? Well, so one place where it comes up is when we try to understand whether a vector field is conservative. Remember, we've seen that a vector field is conservative if and only if its curl is 0. So that's the situation in which we're allowed to try to look for a potential function and then use the fundamental theorem. But another place where this comes up, if you remember what we did in the plane, curl also came up when we tried to convert line integrals into double integrals. That was Green's theorem. So it turns out we can do the same thing in space, and that's called Stokes' theorem. Okay, so what does Stokes' theorem say? It says that the work done by a vector field along a closed curve can be replaced by a double integral of curl f. Let me write it using the del notation. In case you prefer, that's curl f dot n ds on a suitably chosen surface. So that's a very strange kind of statement, but actually it's not much more strange than things we've seen before. So I should clarify what this means. So C has to be a closed curve in space. And S can be any surface bounded by C. Okay, so for example, what Stokes' theorem tells me is that let's say that I have to compute some line integral on maybe, say, the unit circle in the xy plane. Okay? Of course, I can set up the line integral directly and compute it by setting, x equals cosine t, y equals sine t, z equals 0. But maybe sometimes I don't want to do that because my vector field is really complicated. And instead, I will want to reduce things to a surface integral. Now, I know that you guys are not necessarily fond of computing flux of vector fields for surfaces, so maybe you don't really see the point. But sometimes it's useful. Sometimes it's also useful backwards, because actually you have a surface integral that you'd like to turn into a line integral. So what Stokes' theorem says is that, if I can choose my favorite surface whose boundary is this circle. So I could choose, for example, a half sphere if I want. Or I can choose, well, let's call that S1. Or I can choose, I don't know, a pointy thing, S2. Or I can choose, probably The most logical one actually would be just to choose a disk in the xy plane. That would probably be the easiest one to set up for calculating flux. But anyway, what Stokes' theorem tells me is I can choose any of these surfaces, whichever one I want, and I can compute the flux of curl F through this surface. So curl F is a new vector field, right? When you have this formula that gives you a vector field, you compute its flux through your favorite surface, and you should get the same thing as if you had done the line integral for F. Okay? That's the statement. Now, there's a catch here. What's the catch? Well, the catch is we have to figure out what conventions to use. Because remember, when we have a surface, there's two possible orientations. So we have to decide which way we will count the flux positively, which way we will count flux negatively. And if we change our choice, then of course the flux will become the opposite. Well, similarly, to define the work, I need to choose which way I'm going around my curve. If I change which way I go around the curve, then my work will become the opposite. So what happens is I have to orient the curve C and the surface S in compatible ways. So we have to figure out what's the rule for how the orientation of S and that of C relate to each other. Okay, so what about orientation? Well, we need the orientations of C and S to be compatible, and I have to explain to you what the rule is. So the rule is, okay, let me show you a picture. So the rule is if I walk along C with S to my left, then the normal vector is pointing up for me. Okay, let me write that. If I walk along C, I should say in the positive direction, in the direction that I've chosen to orient C. With S to my left, then N is pointing up for me. Okay, so here's the example. If I'm walking on this curve, it looks like the surface is to my left, and so the normal vector is going towards what's up for me. Okay. Any questions about that? Yeah, I see some people using the right hand. There's also a right hand rule, which I'm going to say in just a few moments. That's another way to remember this. But okay, so before I tell you about the right hand rule version, let me just clarify something. So let's say that I'm actually not happy with this orientation of C, and I want to orient my curve C going clockwise on the picture, so the other orientation. Then if I walk on it this way, the surface would be to my right. So you can remember, if it helps you, that if the surface is to your right, then the normal vector will go down. The other way to think about it, this rule is enough, because if you're walking clockwise, well, you can change that to counterclockwise just by walking upside down. Okay? So this guy is walking clockwise on C, and, well, for him, if you look carefully at the picture, for him, the surface is actually to his left. Right? When you flip upside down, yeah, it's kind of confusing. But anyway, I just want to point out, okay, so maybe it's easier if you actually rotate the entire picture. And now it's getting actually really confusing because, well, so he's walking upside up with, actually, the surface is to his left. I mean, where he is here is actually at the front. and this is the back. But that's kind of hard to see. So anyway, whichever method will work best for you, perhaps it's easiest to first do it with the other orientation, this one, and then decide that if you want the opposite one, then you'll just flip everything. Okay. Now, what's the other way of remembering this with the right-hand rule? So with the right-hand rule, so first of all, take your right hand, not your left hand. Even if your right hand is actually using a pen or something like that, you need your right hand to do this. And let's take your fingers in order. So first your thumb. Let's make your thumb go along the object that has only one dimension in there. That's the curve. Okay? So put your finger, well, let's look at the top picture up there. Okay? So I want my thumb to go along the curve. So that's kind of towards the right. Then I want to make my index finger points towards the surface. So towards the surface, I mean towards the interior of the surface from the curve, right? When I'm on the curve, I'm on the boundary of the surface. So there's a direction along the surface that's the curve, and the other one is pointing into the surface. So that one would be pointing kind of to the back, slightly up maybe, okay? So like that. And now your middle finger is going to point in the direction of a normal vector. That's up, at least if you have the same kind of right hand as I do. Okay, so the other way of doing it is using the right-hand rule. Thumb along C positively. The index finger towards the interior of S. Sorry, I shouldn't say the interior. Maybe I should say tangent to S towards the interior of S. So what I mean by that is really the part of S that's not its boundary. Okay, so the rest of the surface. Then the middle finger points parallel to N. Okay? So let's practice. Let's say that I give you this curve bounding this surface. Which way do you think the normal vector will be going? Up, yes, everyone's voting up. Okay, imagine that I'm walking around C, S is to my left, normal vector points up. Imagine that you put your thumb along C, your middle finger towards S, your index towards S, then your middle finger points up. Very good. So, N points up. Okay, another one. Okay, it's interesting to watch you guys. I think mostly it's going up. So the correct answer is it goes up and into the cone. Okay, so how do we see that? So, well, one way to think about it is imagine that you're walking on C, on the rim of this cone. So you have two options. Imagine that you're walking kind of inside, or imagine that you're walking kind of outside. If you're walking outside, then S is to your right. That doesn't sound good. So let's say instead that you're walking on the inside of the cone, following the boundary. Well, then the surface is to your left. And so the normal vector will be up for you, which means it will be pointing slightly up and into the cone. Okay? Another way to think about it, do the right-hand rule. Thumb this way, index going kind of down because the surface goes down and a bit to the back, and then the normal vector points up and in. Yet another way, if you deform continuously your surface, then the conventions will not change. See, this is kind of topology in a way. You can deform things, nothing will change. So what if we somehow, flatten our cone, push it a bit up so that it becomes completely flat? Then, if you had a flat disk with the curve going counterclockwise, the normal vector would go up. So now take your disk with its normal vector sticking up. If you want to paint the top face, of a different color so that you remember that was the side with the normal vector, and then push it back down to the cone, you'll see that the painted face, the one with the normal vector on that side, is the one that's inside and up. Okay, does that make sense? Anyway, I think you have just to play with these examples for long enough and get it. Okay, a last one. Let's say that I have a cylinder. So now this guy has actually two boundary curves, C and C prime. And let's say I want to orient my cylinder so that the normal vector sticks out. How should I choose the orientation of my curves? Okay, so let's start with, let's say, with the bottom one. Would the bottom one be going clockwise or counterclockwise? Yeah, most people seem to say counterclockwise, and I agree with that. Okay, so let me write that down. I claim C prime should go counterclockwise. One way to think about it, actually, it's pretty easy. Imagine that you're walking on the outside of a cylinder along C prime. If you want to walk along C prime so that the cylinder is to your left, that means you have to actually go counterclockwise around it. Okay. The other way is use your right hand, thumb. So say when you're at the front of C prime, your thumb points to the right. Your index points up because that's where the surface is. And then your middle finger will point out. Okay, what about C? Well, C, I claim we should be doing clockwise. Okay? I mean, think about just walking again on the surface of a cylinder. Along C, if you walk clockwise, you will see that the surface is to your left. Or use the right-hand rule. Okay? So now, if a problem gives you neither the orientation of the curve nor that of the surface, then it's up to you to make them up. But you have to make them up in a consistent way. You can't choose them both at random. Okay? All right. So now we're all set to try to use Stokes' theorem. So, well, let me do an example first. The first example that I will do is actually a comparison Stokes versus Green. Okay. So I want to show you how Green's theorem for work that we saw in the plane, that also involved work and curl and so on, is actually a special case of this. Okay. So let's say that we'll look at the special case where our curve C is actually a curve in the xy plane. And let's make it go counterclockwise in the xy plane because that's what we did for Green's theorem. Okay, now let's choose a surface bounded by this curve. Well, as I said, I could make up any crazy surface that comes to my mind. But if I want to relate to 2D stuff, I should probably stay in the xy plane. So I'm just going to take my surface to be the piece of the xy plane that's inside my curve. Okay, so let's say S is going to be a portion of xy plane bounded by a curve C, and the curve C goes counterclockwise. Well, then I should look at the line integral, so the work along C of my favorite vector field f.dr. So that will be the line integral of p dx plus q dy. I guess if I call my components, components of my field p, q, and r, it will be p dx plus q dy plus r dz, but I don't have any z here. dz is 0 on C. Okay, so if I evaluate the line integral, I don't have any term involving dz. Z is 0. Now let's see what Stokes says. Stokes says instead I can compute the flux through S of curl F but now, what's the normal vector to my surface? Well, it's going to be either k or negative k. I just have to figure out which one it is. Well, if you've followed what we've done there, you know that the normal vector compatible with this choice for the curve C is the one that points up. Okay, so my normal vector is just going to be k hat. Okay, so I'm going to replace my normal vector by k hat. So that means actually I will be integrating curl.k. That means I'm integrating the z component of curl. Okay, so let's look at curl f dot k. That's the z component of curl f. And what's the z component of curl? Well, I conveniently still have values up there. It's q sub x minus p sub y. Okay, so my double integral becomes double integral of q sub x minus p sub y. What about ds? Well, I'm on a piece of the xy plane, so ds is just dx dy or your favorite combination that does the same thing. So now see, if you look at this equality, integral of p dx plus q dy along a closed curve equals double integral of qx minus py dx dy. That's exactly the statement of Green's theorem. Right? I mean, except at that time we called things m and n, but really that shouldn't matter. Okay, so this tells you that in fact Green's theorem is just the special case of Stokes in the xy plane. Okay. Now, another small remark I want to make, by the way, before I forget. So you might think that, these rules that we've made up about compatibility of orientations, they are completely arbitrary. Well, they're arbitrary in the same way as our convention for which guy we call curl is arbitrary. We chose to make the curl be this thing and not, the opposite, which would have been pretty much just as sensible. And ultimately, that comes from our choice of making the cross product be what it is rather than the opposite. So ultimately, it all comes from our preference for right-handed coordinate systems. If we had been on a planet with left-handed coordinate systems, then actually our conventions would be all the other way around. But they are this way. Okay. Any other questions? Yes?
kind of surface you would
So a surface that you use in Stokes' theorem is usually not going to be closed because its boundary needs to be the curve C. So if you had a closed surface, you wouldn't know where to put your curve. I mean, of course, you could make a tiny hole in it and get a tiny curve. So actually what that would say, and we're going to see more about that, so not very important right now, but what we would see is that for a closed surface, we would end up getting 0 for the flux. And that's actually because divergence of curl is 0. But I'm getting ahead of myself. So we're going to see that probably tomorrow in more detail. Yes?
Does Stokes still work if the map is not used algebra?
That's a very good question too. No, Stokes' theorem only works if you can make sense of this. So that means if you need your vector field to be continuous and differentiable everywhere on the surface S. Okay, so now, why is that relevant? Well, say that your vector field was not defined at the origin, and say that you wanted to do the example that I had first with the unit circle in the xy plane. So normally, the most sensible choice of surface to apply Stokes' theorem to would be just the flat disk in the xy plane. But that assumes that your vector field is well defined there. If your vector field is not defined at the origin, but defined everywhere else, you can't use this guy. But maybe you can still use, say, the half sphere, for example. Or you could use a piece of cylinder plus a flat top, or whatever you want, but not passing through the origin. So you could still use Stokes, but you'd have to be careful about which surface you choose. Now, if instead your vector field is not defined anywhere on the z-axis, then you're out of luck, because there's no way to find a surface bounded by this unit circle without crossing the z-axis somewhere. So then you wouldn't be able to use Stokes' theorem at all, or at least not directly. Yeah, so the implicit thing, and I should say, okay, so maybe I should write it. And F defined and differentiable everywhere on S. Okay? But we don't care about what happens outside of S. It's really only on the surface that we need it to be okay. I mean, again, 99% of the vector fields that we see in this class are defined everywhere. So that's not a very, it's not an urgent concern, but still. Okay, should we move on? Yes, I heard a yes. Okay, so let me explain to you quickly why Stokes is true. So how do we prove a theorem like that? Well, the strategy, I mean, there's other ways, but the least painful strategy at this point is to observe that we already know a special case of Stokes' theorem. Namely, we know the case where the curve is actually in the xy plane, and the surface is a flat piece of the xy plane, because that's Green's theorem, which we bothered to prove a while ago. So first thing is we know it for C and S in the xy plane. Now, what if C and S were, say, in the yz plane instead of the xy plane? Well, then it wouldn't quite be the same picture, because the normal vector would be I hat instead of k hat, and I would be having different notations, and I would be integrating with y and z, but you see that it would become, again, exactly the same formula. So we'd know it for any of the coordinate planes. In fact, I claim we know it for absolutely any plane. And the reason for that is, sure, when we write it in coordinates, when we write, that this line integral is integral of p dx plus q dy plus r dz, or when we write that the curl is given by this formula, we use the xyz coordinate system. But there's something I haven't quite told you about, which is if I switch to any other right-handed coordinate system, so I do some sort of rotation of my space coordinates, then somehow the line integral, the flux integral, the notion of curl makes sense independently of coordinates. And the reason is that they all have geometric interpretations. For example, when I think of this as the work done by a force, well, the force doesn't care whether it's being put in xyz coordinates this way or that way. it still does the same work because it's the same force. And when I say that the curl measures the rotation in a motion, well, that doesn't depend on which coordinates you use. And same for the interpretation of flux. So in fact, if I rotated my coordinates to fit with any other plane, I could still do the same things. So what I'm trying to say is, in fact, if C and S are in any plane, then we can still claim that it reduces to Green's theorem. Just it will be Green's theorem not in x, y, z coordinates, but in some funny rotated coordinate systems. So what I'm using is that work, flux, and curl make sense independently of coordinates. Now, I mean, this has to stop somewhere. I can't start claiming that I can, somehow bend my coordinates to claim that any surface is flat. That doesn't really work. But what I can say is if I have any surface, I can cut it into tiny pieces. And these tiny pieces are basically flat. So that's basically the idea of a proof. I'm going to decompose my surface into very small flat pieces. So given any S, we are just going to decompose it into tiny, almost flat pieces. So, for example, if I have my surface like this, what I will do is I will just, cut it into tiles. I mean, a good example of that is, if you look at those geodesic things, or if you look like, at a soccer ball, for example, it's made of all of these, hexagons and pentagons. And, well, actually, they're not quite flat on the usual ball, but you could make them flat, and it would still look pretty much like a sphere. So anyway, you're going to, cut your surface into lots of tiny pieces, and then you can use Stoke's theorem on each small piece. What it says on each small flat piece, that's where my chalk is. It says that the line integral along, say, for example, this curve is equal to the flux of the curl through this tiny piece of surface. And now I'll add all of these terms together. If I add all of the small contributions to flux, I get the total flux. What if I add all of the small line integrals? Well, I get lots of extra junk because I never asked to compute the line integral along this. But this guy will come in twice when I do this little plate and when I do that little plate with opposite orientations. So when I sum all of the little line integrals together, all of the inner things cancel out. And the only ones that I go through only once are those that are at the outermost edges. So when I sum all of my works together, I will get the work done just along the outer boundary C. Okay, so sum of work around each little piece is just actually the work along C, the outer curve. And the sum of the flux through each piece is going to be the flux through S. So from Stoke's theorem for flat surfaces, I can get it for any surface. I'm cheating a little bit because you'd actually have to check carefully that this approximation where you flatten the little pieces that are almost flat is valid. But Trust me, it actually works. Okay. So, is there a question that no? Okay, so let's do an actual example. I mean, I said example, but that was more like getting us ready for the proof, so probably that doesn't count as an actual example. I should probably keep these statements for now, so I'm not going to erase this side. Okay, so let's do an example. Let's try to find the work of a vector field zi plus xj plus yk around the unit circle in the xy plane, counterclockwise. So the picture is conveniently already there. So just as a quick review, let's see how we do that directly. Well, if we do that directly, I have to find the integral along C of, so f dot dr becomes z dx plus x dy plus y dz. But now we actually know that on this circle, well, z is 0, and we can parameterize x and y. It's the just unit the unit circle in the xy plane. So we can take x equals cosine t, y equals sine t. Okay, so that will just become the integral over c. Well, z times dx, z is 0, so we have nothing. Plus x is cosine t times dy is, well, if y is sine t, then dy is cosine t dt, plus y dz, but z is 0. Now, the range of values for t, well, we're going counterclockwise around the entire circle, so that should go from 0 to 2 pi. So we'll get integral from 0 to 2 pi of cosine square t dt, which, if you do the calculation, turns out to be just pi. Okay? Now, let's instead try to use Green's theorem Stoke's theorem to do the calculation. So now, of course, the smart choice would be to just take the flat unit disk. I'm not going to do that. That would be too boring. Plus, I mean, we already kind of checked it because we already trust Green's theorem. So instead, let's say, just to convince you that, yes, I can choose really any surface I want, let's say that I'm going to choose a piece of paraboloid z equals 1 minus x squared minus y squared. Okay? And, well, to get our convention straight, observe that we should take the normal vector pointing up for compatibility with our choice. So, well, we'll have to compute the flux through S. I mean, we don't really have to because we could have chosen the disk. It would be easier. But if we want to do it this way, we'll compute the flux of curl F through our paraboloid. So how do we do that? Well, we need to find the curl, and we need to find NDS. Okay, let's start with the curl. So curl F, let's take the cross product between del and F, which is ZXY. Okay, so if we compute this, the I component will be 1 minus 0, it looks like it's 1I, minus the J component is 0 minus 1, plus the K component is 1 minus 0. So in fact, the curl of this field is 1, 1, 1. Okay? Oops. Now, what about NDS? Well, this is a surface for which we know Z as a function of x and y. So NDS we can write as, so let's call this f of xy. Then we can use the formula that says NDS equals negative f sub x, negative f sub y, 1 dx dy, which here gives us 2x, 2y, 1 dx dy. So now when we want to compute the flux, we'll have to do double integral over S of 1, 1, 1 dot product with 2x, 2y, 1 dx dy. It will become the double integral of 2x plus 2y plus 1 dx dy. And of course, the region over which we're integrating, the range of values for x and y, will be the shadow of our surface. So that's just going to be, if you look at this paraboloid from above, all you'll see is the unit disk. So it will be a double integral over the unit disk. And the way we'll do that, so one way is to switch to polar coordinates and do the calculation, and then you will end up with pi. The other way is to try to do it by symmetry. Observe when you integrate x over this, x is as negative on the left as it's positive on the right. So the integral of x will be 0. The integral of y will be 0 also by symmetry. Then the integral of 1 dx dy will just be the area of this unit disk, which is pi. Okay, so that was our first example. And of course, if you're actually free to choose your favorite surface, there's absolutely no reason why you would actually choose this paraboloid in this example. I mean, it would be much easier to choose a flat disk. Okay, so tomorrow I will tell you a few more things about how curl fits in with conservativeness and with the divergence theorem, Stokes all together. And we'll look at practice exam 4B. So please bring the exam with you.